Hi everyone, I'm Russell Deitrick. I'm a postdoc in the Hang group in Bern. I'll be talking a bit about the development of our GCM called Thor and the challenges, limits, and lessons that we've learned. I am relatively new to the GCM world, so I apologize in advance if much of what I say is mundane or pedagogical. But sticking with the theme of this session, I will be discussing a lot of modeling issues as I understand them, and I'll start with a brief introduction to the Thor GCM. So as I said, Thor is a GCM. It is based primarily on algorithms from Tomita and Sato, although there's a number of other works that have influenced the design. It is non-hydrostatic and deep, meaning that we aren't by default making the quasi-hydrostatic or shallow approximations, but those are available as options if one desires to do comparisons. It is coded from scratch to avoid Earth-centric hard codings and to code for GPUs so that we can have nice, easy parallelization. Most of the code was written by Joao Mendonça, but with large contributions from Simon Grimm, Urs Schroffenegger, and myself, and of course the scientific support of our research group. We are using an icosahedral grid, which is just an icosahedron, 20-sided solid with triangular faces, and we subdivide those triangular faces into ever smaller and smaller triangles to approximate the spherical geometry. And this grid nicely circumvents some numerical issues that are common at the poles that I will briefly touch on later. Primarily, we've applied the model to hot Jupiter so far, and I'll be talking mainly about results for this type of planet, so I briefly wanted to provide an overview of the main features that we see. This is from a simulation of HT 189.733b. On the left, I'm showing the temperature and horizontal winds at a level of 0.1 bar, and on the right, the zonally averaged zonal wind speed. So some of the things we see are an eastward hotspot offset of 30 to 40 degrees from the substellar point, a standing wave pattern of Rossby and Kelvin waves, and strong equatorial superrotation reaching several kilometers per second. And these are the main features that we see in most GCM simulations and are generally consistent with the observations that we have. Now I'll get into some of the issues that I've experienced with Thor or seen in other GCMs. One important thing to consider is, of course, conservation of various properties, and perhaps the most important is conservation of mass. Now, finite volume models like ours should conserve mass very well if the code does not have any bugs, and I have personal experience here because we did have a bug that led to poor mass conservation and weaker winds in older versions of the model. Because of the atmospheric pressure loss, we have weaker wind speeds. But now we are conserving mass very nicely to close to machine precision. Now, I have no experience with spectral codes, but I understand that often these models need mass correctors to prevent long-term pressure changes in the atmosphere. Angular momentum is also something to consider as a conserved property. And I've seen in some simulations where poor angular momentum conservation at just small drifts can lead to some very strange results. Now in this plot here, I'm showing a zonally average temperature in the shallow hot Jupiter benchmark case. This is just a hot Jupiter with a very shallow atmosphere kind of test simulation. And basically, after about 7,000 days of integration, this simulation saw a drift in the angular momentum that leads to this strange asymmetry that you see here at the bottom of the model. So it's important to consider these kinds of things. They can lead to strange results. I don't know exactly what the origin of this shift is, but I suspect that with a better resolution or time step, we would be able to resolve this conservation issue a bit better. I wanted to briefly discuss the sensitivity to numerical settings, which is a potential issue in hot Jupiter simulations. Here, I'm comparing the maximum zonal wind speed for simulations run in different modes, so non-hydrostatic, quasi-hydrostatic, and fully hydrostatic. and with different values for the numerical diffusion strength at 2 different resolutions. There's some spread in the peak wind speeds, as you see here, though if we look at the predicted phase curves, the integrated flux that would be observed due to thermal emission by an observer, this is relatively insensitive to these numerical settings. Another issue that is common to many GCMs that I briefly mentioned earlier is this pole problem. And in Thor, we specifically chose this icosahedral grid to avoid this issue. But because of crowding of volume elements in the latitude-longitude grid, this polar region is often a problem. There are various solutions. Using a different grid is one obvious idea, but there's also filters and damping mechanisms that are used in different models to solve this. But this problem is particularly important for hot Jupiters because we have very, very fast flows in the polar regions of these planets. One particularly troublesome solution to this is an avoidance strategy. This model from Ian Dobbs-Dixon just omitted the polar regions in the hot Jupiter simulations entirely. And Kevin Hang has always been very critical of this approach. And recently I found that criticism was somewhat validated when I was talking to a student of Xi Zhang's named Huazi Ge. And their model, they were running this shallow hot Jupiter benchmark and finding very different results when they omitted the polar regions. So it's sort of validating our choice of a grid to solve this problem. Another issue that is often discussed in hot Jupiter modeling is initial conditions. This first point I have is perhaps not so surprising or interesting, but what I have discovered is that the initial PT profile has a very strong effect on the stability. And in particular, if we initialize from what we call Guillot profiles rather than isothermal initial conditions, Guillot profiles are a bit closer to radiative equilibrium. And so at the beginning of the simulation, the forcing is not quite so strong. And so we are less prone to model crashes. Now, there's another interesting result that I saw, which is not from our model, it's from a different group, that the initial deep atmospheric profile can affect the jet speed. This was presented by Sainsbury Martinez at Exoplanets 3, and what they were finding was that if they initialize the deep atmosphere with an isothermal structure rather than an adiabatic structure, they have an increased wind speed in the upper atmosphere. And I think this has to do with the fact that an adiabatic atmosphere will suppress gravity waves and you won't have so much angular momentum transfer between the deep and the upper atmosphere. As the title says here, convergence is slow for very deep atmospheres, such as hot Jupiters. One way to measure convergence is via the superrotation index introduced by Peter Reed. Again, I'm showing results for HC189 under various numerical settings, and we call the model fully converged, at least in terms of flow, when this superrotation index plateaus. And you can see that this happens within a few thousand days of integration for the simulations at the very coarse 4-degree horizontal resolution. But the 2-degree resolution simulations, which are these two curves, are still not converged. And I expect that the problem becomes even worse at a higher resolution. So it can be really time consuming to integrate these to fully steady state, especially with wavelength dependent radiative transfer. Now, very little is actually changing in the upper atmosphere of these simulations. Rather, what is happening is that the deep atmosphere is still gradually accelerating. Basically, this jet is extending deeper and deeper. Now, I haven't included any additional drag parameterization for the deep atmosphere, but there's reason to think that there should be some kind of magnetic drag. And the side effect of this would be that it would also help improve our convergence. Now, I wanted to lastly mention some things about issues that I think of as unresolved. At least I don't have a good solution to them. So we have reflecting boundary conditions in the model, and thus we need to have sponge layers. And sometimes for hot Jupiters, these are necessary just to even run the model because the gravity waves are so strong, so strongly reflected off the top boundary. And the physics isn't really correct with or without the sponge. Both cases, we have something artificial going on in the model. But the good news is at least that if we compare simulations with and without the sponge layer, at least in the zonal flow, we're seeing pretty similar patterns, although the velocities are slightly higher in the case without the sponge layer. But our observations are not quite ready to distinguish these cases yet. Another issue is that of shock capture. So there's some expectation that because we have supersonic winds and hot Jupiters that we should see shocks, but there's some debate about whether or not these should actually be present, whether or not you have all the conditions just right for shock formation. We're not able to model this in Thor. We don't have a shock capture scheme, so we know that this is a potential issue. And we've chosen to use an entropy equation in Thor, which it turns out is not the best case when you have a strongly variable heat capacity, but I don't have time to get into the details there. I want to end by saying that we are, well, just summarizing that Thor is a relatively new general circulation model for exoplanets, and we've used it for hot Jupiters with some success, but we have, of course, remaining challenges. We have an ERC grant in my group to study terrestrial planets orbiting cool stars, so I'm working towards that. And with that in mind, if I can get there in time, may already be too late, I don't know, but if I can get the physics done in time, I would like to join the TIE intercomparison. And with that, I'll end. Thank you.